There's another major style of proof, which we're going to present as a rule of inference, which is the sort of final major style for now, in addition to direct and indirect proof. It's called proof by cases. Proof by two cases is as follows. Notice that this is a rule of inference with three hypotheses. Specifically, two of them are conditional statements that have the same conclusion, in this case R. There's also a disjunction, which is very specifically the two hypotheses, P and Q. As always, these could be compound statements. They could involve other things. The basic rule is two conditional statements with a shared conclusion, and then whatever these hypotheses are, they show up as a disjunction. If you have all three of these pieces, you can extract the conclusion R must be true. Now the proof is not so bad. Okay, so here it is. We state our three givens. Here's our desired conclusion R. It's not a conditional statement, so we're going to do an indirect proof, so we assume not R. Well, since I have not R, I can apply modus tollens twice and extract both not P and not Q. So I can conjoin those and say, well, I have not P and I have not Q. By De Morgan's law, this is the negation of P or Q. But one of our givens was P or Q, so I can conjoin that given, P or Q, with what we just derived, the negation of P or Q. And now we have a contradiction, something, namely this disjunction P or Q, and its exact negation. So we have concluded the justification of that assertion, which means the proof of this is complete. This is a valid rule of inference. So whenever you have two conditional statements with the same conclusion, also a disjunction of the two hypotheses, you can use the rule of inference proof by cases, refer to those three lines, and derive the conclusion R. So let's see an example of using proof by cases. Okay, so this proof starts much as we would expect. Okay, we state the three hypotheses and call them givens. Now I'm going to assert that P implies Q or R. It's not immediately obvious why I would do that, I agree. But what type of statement can you assert? Anything you want. So there it is. This is a conditional statement, so I'm going to start the proof of this conditional statement by assuming its hypothesis. Since I have P, that's going to give me some stuff to work with. Specifically, by applying modus tollens with line 2, I can get out to Q. Since I have Q, I can get out the generalization Q or R. Why did I want this? Well, remember, we were doing a direct proof of this conditional statement assertion. So once I assume its hypothesis, it will be completed if I can just get the conclusion Q or R. Getting out Q is good enough. If you know Q is true, then definitely Q or R. So that backs up this assertion. This is now a statement that I know to be true, but I can't refer to these lines in the black box. But I can keep going with a proof. I can make another assertion. Specifically, I'm going to assert that not P implies Q or R. What type of statement can I assert? Anything I want, but I have to now back it up. Since it was a conditional statement, I can try a direct proof, so I assume its hypothesis, not P. Well, since I have not P, I can resolve the given in line 1. If I don't have P, then I must have had A. But I can also apply De Morgan's law to line 3 and extract not A or R. I can now do a resolution of A with not A and get out R. Now that I have R, I can generalize to Q or R. Very similarly to before, from the assumption of this hypothesis, I need to get to the conclusion, Q or R. Since I got out R, I can just generalize that. That backs up that assertion there. So now P implies Q or R, and not P also implies Q or R. But it's a tautology that either P or not P is true. That's just the law of the excluded middle. So now look what we have. Two conditional statements that have the same conclusion. We also have a disjunction of the two hypotheses. So by applying proof by cases, if I have two conditional statements with the same conclusion, and I know that either one of the two hypotheses is true, what I extract is the shared conclusion. And Q or R is exactly what we were trying to get. So this is a little roundabout way of doing it, and it's certainly not the only approach, but it is legitimate. We have legitimately derived the conclusion Q or R. Let's work through another example. So we begin by stating our three givens. Okay, 1, 2, 3, there they are. Now what we need to do is make the statement S appear. Now what we could do is we could simply assert S and do an indirect proof. Okay, it will actually not be that bad to do so, but we're trying to practice proof by cases. So here's how we're going to do that. All right, here's a sort of framework of what's coming. Observe that we're trying to get out S. The contrapositive of line 3 is that not Q implies S. So I can get this statement, not Q implies S. And it's definitely a tautology, either Q or not Q. So both of these lines can be introduced wherever I want. If I want to apply proof by cases to extract S, if not Q implies S and either I have Q or I don't, the missing piece of that puzzle is to show that Q implies S. So that's why it's here as an assertion. If I can justify this assertion, then I will have Q implies S, not Q implies S, and either Q or not Q, so proof by cases will get out our desired S. That will complete the proof. But we do have to back up this assertion. Now, this will vary from instructor to instructor, but if you just presented this to me, you would get nearly full credit because you have demonstrated you know what pieces of the puzzle will fit together to finish the problem. You'll get even more credit if you do this. Since I have made an assertion that is a conditional statement, we move to a subnumber and let's go ahead and try a direct proof. And with Q, it's pretty apparent that I can go ahead and use modus ponens to extract P or S. Now we're not done with this proof. Having assumed Q, the hypothesis of this conditional statement, we need to make S appear. If I can make S appear, that will back up the proof of Q implies S, and then the proof by cases will fall together. But still, we've shown a lot of initiative, and we've shown that we can put together a few meaningful steps. But let's go ahead and keep working. So what I really want is to get out S, because that's the conclusion here. And maybe I've run out of ideas on how to do it, so I can assert it. So I immediately pass to a subnumber. From line 4.3, we go to 4.3.1. This was not a conditional statement, so I had better assume its negation. Now, I cannot refer to line 4.3 because it hasn't been proven yet, and I can't refer to line 4, but I can use lines 4.1, 4.2, and of course the givens. So with line 1, having assumed not S, I can resolve that and get out P implies S. But now I can use modus tollens between these two lines and get out not P. Now that I have not P, I can resolve that with line 4.2 and extract S. And now I've got two contradictory things, the not S I assumed and S. So I can conjoin them to get a contradiction. That backs up this assertion. So now I know that having assumed Q, I really could proceed to S, which itself backs up this assertion. Now that line 4 has a complete proof, I can do proof by cases using lines 4, 5, and 6. We've already remarked how 5 and 6 are derived, and this proof is now complete. Okay, of course there are other ways to do this, but this is just a way to use proof by cases. I also want to point out that once you finish this assertion, you're not actually done. Even though the proof is done when you have the line S, line 4.3 is not really its own independent line. It's part of backing up line 4. So just getting an S here does not end the proof. Of course, you could state the three givens and then assert S and start an indirect proof straight off. But this was just a way to make a proof by cases show up for the sake of practice. Having discussed how to do proof by cases, there's a new rule of inference we can introduce, which is very similar. Suppose P implies S, Q implies S, and R implies S, but also you have one of the three, P, Q, and R. Since any one of them would imply S, and you do have one of them, you conclude S. There are now 4 different hypotheses, 3 conditional statements that have the exact same conclusion, plus a disjunction of the 3 hypotheses. It's proved pretty straightforwardly. We state our 4 givens. Okay, those are lines 1, 2, 3, and 4. In line 5, I conjoin lines 1 and 2, but I can then use a distributive property to say this. The associative property on line 4 says I can put the parentheses wherever I want. And now notice what we have. P or Q implies S, R implies S, and either P or Q or R, which is really just proof by 2 cases, using lines 3, 6, and 7. two conditional statements with the same conclusion. Then I take their hypotheses and I have them disjoined. So even though this looks like a new rule, it's really just proof by two cases with a little extra step. Okay, so this associativity line is not strictly necessary, but I wanted to make clear that the line P or Q or R can be interpreted either with parentheses around the Q or R, or it can be interpreted with parentheses around the P or Q. The associative property says those two are the same thing. All right, here's another example of working through cases. And we've started off by stating our givens. It's a pretty reasonable place to start. There are a lot of ways we could proceed. For example, you could simply state B as an assertion and start an indirect proof. But that's not how we're going to do it because we're trying to practice cases. Specifically, I already know A implies B. Let's suppose that X implies B and Y implies B. I don't necessarily know how to justify these yet. Okay, then I'm going to claim I can do a proof by cases combining lines 6, 7, and 1. A implies B, X implies B, Y implies B, and a missing line 8. Well, if I want to go from A implies B, X implies B, Y implies B, and I want to conclude B, what's the missing line? It's got to be the disjunction of those three hypotheses, X, Y, and A. In any particular order, it doesn't matter. Now I need to justify these things here. Okay, a missing step that helps get me from one to the other is to apply De Morgan's law to line 2. Not X or B. But that's just a conditional equivalence. If X is false or B is true, then X implies B. Either the hypothesis is false or the conclusion is true. I can also combine lines 1 and 3. Y implies A and A implies B, so by transitivity, Y can be used to imply B. Why is line 8 justified? Well, look at line 4. Y is false or, not Y implies A or X. So a conditional equivalence would say either the hypothesis is false or the conclusion is true. And again, we could have parentheses around this, like that. Either the hypothesis is false or the conclusion is true. But by the associative property, it doesn't matter where I put these parentheses. So you can kind of just drop them as long as you only have one symbol here. They're both disjunctions. So then I can combine A implies B, X implies B, Y implies B. Also, one of those three things has to be true. Therefore, B is true. So here's a proof that involves three cases. In general, proof by cases can be extended a whole bunch. So it's not limited to either 2 or 3 cases. Suppose you have some collection of statements. One hypothesis, P1, implies R. A second hypothesis, P2, implies R. And that keeps going for a while until some nth hypothesis, P sub n, implies R. And you also have a disjunction of all of those hypotheses together, P1 or P2 or, and all the way up to P sub n. A lot of times this is some sort of tautology. It doesn't have to be, however. Then you can derive the conclusion. So for 2 cases, it's just P1 implies R, P2 implies R, P1 or P2, therefore R. For 3 cases, you'd have a third one, but then you need an extra thing in your disjunction line. But that can keep going. Now, most people are pretty willing to believe this. The reason I'm not going to be too formal about it is that we haven't really introduced the logical language necessary to state things about any number of statements. Any number of things. We haven't even really discussed what numbers are or how to approach them. So since we don't have the formal language to discuss this, we're not going to be too precise about it. Okay, but think back to how we showed that proof by 3 cases was a legitimate rule of inference. We started from proof by 2 cases and did a little associativity trick. You can do the same thing and say, well, now that I know proof by 3 cases works, I can do a little associativity trick and show that proof by 4 cases works. And then you can do it again to get to 5 and so forth. So any number of cases can work, but we're not going to prove that very formally. Also, it's pretty rare in an introductory course like this for anything more than 3 cases to be used. Out in the real world, proofs frequently have very, very many cases, and it can be rather tedious to keep track of them all. But in an introductory logic course like this, 2 or 3 cases is usually about where people cut it off.